the two boundary map is going to be A equal to minus B, right? I mean, it's, how can I say this? I mean, it maps to these things, right? That's not right either. I mean, it should be.
They say the kernel is 0.
They say the kernel's 0?
Yeah. So yes, both A and B has to be equal to 0 in that case. Since they're
Oh,
kind of,
these are. I'm not thinking of this the right way. I should think of this more like.
because they're kind of like independent, right?
More like that.
Right, because the points.
I mean, this is.
Well,
No?
I don't think so. But it's kind of like.
Well, it's essentially the same thing.
Kind of like they're kind of linearly independent, so they both have to be 0 in that case.
Oh. Okay. Right.
I'm not sure. I don't know.
Yeah. If this equals to 0 and A and B are linearly independent, that forces. Well.
Yeah. I don't understand this.
Something like it should be some. I mean, I think we should be looking at something like MA plus NB, such that M and N are integers, right? And
Well,
also 2A plus 2B is equal to 0.
well, the kernel of the boundary is going to be a subset of the group generated by P. So
Mm-hmm.
it's just like anytime that it's like some non-zero number times P, you're gonna get some sum of A and B, which is never gonna be 0, unless P is equal to 0, or unless it's 0 times P, I guess. So like if you take the boundary of like MP, M times P, where M is some integer,
Oh, okay.
right? It's
Yeah.
going to be 2M times A plus B,
Mm-hmm.
which is only going to be equal to 0 when M is equal to 0.
Okay.
Therefore, the kernel has to be 0 times P.
Okay. I believe you. And yeah, that makes sense. The kernel.
Yes.
What's the kernel of? I mean the boundary. So. So Z2 equals to 0, and also B2 is equal to 0, right?
Right.
Okay, so like H2 is 0. What's the kernel of boundary 1? Again, I think because V and W are, I think is the kernel 0 again? Oh man.
Here it says that it's generated by A plus B,
Hmm.
which makes sense.
Oh. Yeah, I see that. That makes sense, actually. I mean, if I add these, I get 0. So the boundary 1 of A plus B is 0. So yeah. And what's B? What is is there anything in B1?
Mm-hmm. That says it's the group generated by 2 times A plus B. I don't understand that. Oh wait, no, yeah. So it's from what we got that the boundary of P is 2 times A plus B.
Oh, right.
Yeah.
There. Right. So, cool. So, when you take Z1 mod B1, you're looking at A plus B mod 2 times A plus B. May I speculate that that's Z2?
Yeah.
Right. Yay! I did some math. All right. Sorry, small victories. That's cool. So that's H1. The first homology group of the projective plane is Z2 for these reasons. And then he calculates that what's the last one?
So the kernel is the whole thing. Since we saw that the boundary of W and the boundary of V are both 0. So it's going to be set generated or generated by V plus generated by W. And then the boundary is just the image of.
I'm sorry, I forget about the noise from the hallway. It's like ruined her.
In the moment.
So you're saying so Z naught, the cycles are Z naught, are the sum of both vertices, and the boundary is the difference in the vertices because right here.
Right.
That shows that the difference of the vertices is attained as the image of A or minus B, or vice versa, whichever difference you want to look at.
Yeah, and any combination is just gonna.
So then H naught is going to be, looks like V plus W mod W minus VA.
Just 2Z or Z squared mod Z.
Oh, so this is essentially
Z.
Z plus Z mod Z.
Yeah.
So it's Z. Yeah. Anyway, as he says down here in this remark, it is known, see Massey 1967 chapter 1, that every compact connected two-manifold can be obtained by identifying edges of an even-sided polygon. The method of adequate subcomplexes is thus strong enough to compute their homology groups. And those homology groups can be shown, they can be interpreted in terms of free groups in a really compact, bad word, in a very concise and beautiful way in terms of free groups. And I still want to write that down for you guys more concretely. I haven't found that in this book yet. I'm surprised it's not here. I mean, maybe it's here. I'm just not seeing it. Maybe it's in the, I don't know. So there is, of course, a little bit more interesting stuff in this chapter. Indeed. But I am going to let Nathan pick up next time in the natural transformations chapter. The Searfoot-Van Kampen theorem we saw before, didn't we? Or no?
We looked at it briefly.
Looked at it briefly. So I might need to come back to that another day, but I'm going to let Nathan pick up the next time. And if I have anything more to say, I'll probably say from another book. Since I must admit, I don't have enough time to properly digest and really add to this book right now. Anyway, thanks guys.